Good morning, good afternoon, and good evening to all our attendees joining us today for this latest Data Science Central webinar. This is Bill Voorhees, your host. I'm the Editorial Director with Data Science Central and also Chief Data Scientist for Data Magnum. I'd like to start off our event today by thanking Tableau for sponsoring today's event. Tableau is a longtime supporter of the Data Science Central community, and we're honored to have them sponsoring our event today. I'd also like to take this opportunity to mention and show our appreciation for some of our other recent sponsors, including Alteryx, Teradata, Crowdflower, Exaptive, Qubole, and Dell Statistica, to name just a few. Now, past webinars are available on demand at datasciencecentral.com, and if you haven't had a chance to take a look at them, I encourage you to do that. They provide some very useful insight into a wide variety of topics that are of interest to our data science community. Today's webinar is entitled How Not to Be Wrong About Visualization. And before we begin, I'd like to briefly review the format of today's webinar. So our event today will be an hour long. We have one presenter that I'll introduce in just a minute. We'll save 10 or 15 minutes for Q&A following the presentation. And this event is being recorded and will be available on datasciencecentral.com later this afternoon following today's live event. Now, I'd also like to encourage our attendees to provide questions throughout the presentation. We'll be reviewing and presenting them on your behalf during the Q&A portion of today's event. Now, I'm very pleased to introduce today's speaker, Robert Kisara. Robert is a senior research scientist at Tableau Software and formerly Associate Professor of Computer Science at UNC Charlotte. He's created visualization techniques like parallel sets and performed research into the perceptual and cognitive basis of visualization. Now recently, Robert's research is focused on how to communicate data using tools for visualization and how storytelling can be adapted to incorporate data, interaction, and visualization. Robert received his Master of Science and doctorate degrees in computer science from Vienna University of Technology in Vienna, Austria. Now, many of the things that we take for granted in visualization are based on nothing more than hearsay and may be somebody's aesthetic judgment. Even seemingly obvious things turn out to be wrong when we start to question them. So in today's Data Science Central webinar, you'll learn through a number of examples that show the limits of what we know about visualization. As a particular example, we'll review Robert's recent research into pie charts. How do we read pie charts? Look at any number of books and they'll tell you that we look at the central angle of the slice. That's important because it means that removing the center, like a donut chart, will lead to less accuracy, but it's not true. And worse, this question hasn't been studied since 1926, 90 years ago. It's also one of the most used chart types out there, and yet there are a lot of things we don't know about it. So Robert, with that, I'm going to turn it over to you. You can begin as soon as you're ready to go.
Thank you, Bill. And good morning. I'm going to say good morning, even though I realize many of you are probably not on West Coast time, but it's 9 o'clock here, so I'm going to go with that. So what I'm going to try to do is to talk a little bit about the things we know and the things we don't know in visualization, and to point out a few things that you might think we know, but we actually don't. It's not going to be all negative, though. I'm going to show you actual research and show you a few results here that we've had recently. Since you just saw this horrible picture of me, I figured I'd throw in something a bit better, a bit nicer, and a bit more friendly. It also shows me as the natural leader that I am in one of my runs. Or maybe I'm just running away from the angry mob here because I was talking too much about the pie charts. But what I'm trying to do here today is I want to tell you or to teach you how to ask a question. And that is, how do we know that? When somebody tells you something, you want to know, well, where does this information come from? Is this really established knowledge? Or is that just somebody's opinion? And you'll see that more often than you'd realize, it actually is the latter. And there's a simpler version of this question in case it's a bit too long, which is simply why? Why is this the case? Why do you think this is the case? And I think that's a very useful question to ask, in particular in this field, data visualization, even though it's very young, there's a lot of dogma and a lot of seeming truths here that people just accept, even though there might not be all that much research behind that. So to illustrate what I mean by that, let me show you some fallacies. I'm going to show you 2 or 3 examples here just to kind of give you a quick introduction into what I'm trying to talk about, and then we'll get to the research part of it, or the result of it. So this is a figure from a very famous paper that was published in 1984 by Bill Cleveland and Robert McGill. And it's probably the most cited paper in the visualization literature. And this looks a bit complicated here, but there are 5 different types of bar charts they looked into. They also look at a number of other kinds of charts. But we're mostly going to be interested in these last 2, so what's called type 4 and type 5 here. Those are stacked bar charts. And when you look at those bars more closely, they have little dots in them. And those dots were used back in 1984 or 83, when those studies were actually conducted, to tell people what to look at and which values to compare. And then they were asked to respond by saying, oh, this value is 27% of the other value, or something like that. So they ran this study, and they compared the different types of charts. And you can see here a plot that you will see a few more times in this talk, which shows you what's called the error. This is a particular measure here of error, but basically it shows you the deviation of people's responses when they were asked from the correct value. So if they showed a number of, I don't know, 28% and you guessed 32, then you were off by 4%. And in this case, we don't care about the directions. Whether you were above or below does not actually make a difference. And when you look at the last 2 types here, type 4 and type 5 again in this chart, you can see that the error is the highest. And and I should also explain there are 2 more things. I have another slide that actually explains this chart a little bit better. But the dot here is the mean value of the error. And then the lines are what's called the confidence interval. And this is important because of course there's a lot of variation between people. And so what they look at here is what they would expect with 95% certainty other people to also respond. So basically it gives you a range of what to expect. But the point here is that looking at those last 2, they're much worse than the other charts. So even within the bar charts, you can see that those last 2 types don't overlap in their confidence intervals with the initial ones. There's the first 3, which are just the basic ones where you look at just basic bars. And what's interesting is when you compare that to what they call an angle chart, which is the part that I'm now showing you at the bottom there, which is a pie chart, and you compare those errors, then you can see that the error for the bar chart is actually, for the stacked bar chart, is actually worse than for the pie chart. And that is interesting because that's something that most people don't actually realize, that there are certain types of bar chart, even though the bar chart in general works really well for almost everything, that certain kinds, like certain variations of the bar chart, are actually really bad, especially the stacked bar. And here's an example of what people think about when they think about pie charts. So this is an example I took from Wikipedia because I think it's a really effective one, but it's also a bit misleading. So the idea here is that you look at these 3 pie charts, and you're supposed to compare the green slice. And you're supposed to guess whether the values increase or decrease or stay the same. And when you look at that, you can try it and you can figure out whether you think it's one or the other. But the problem is you're not very certain. It's really hard to be sure about it. You can also pick the yellow one if you want. It doesn't make a huge difference here. And then they compare this to a bar chart. And so this bar chart, of course, works well because it's just single bars. And it's very easy to compare. So this particular kind of bar chart is very effective. But there's an unfair comparison here because we're basically comparing stacked values in the pie chart, or kind of combined values, to very simple bar charts. Now here's an example that I found recently that I think shows quite nicely how difficult the stacked bar chart is, which is a more fair comparison. When you look at this, this is unemployment rates in Bavaria, and the total here is very easy to read. So you can just look at or it's actually not unemployment rate, it's the number of people unemployed over time. And you can see how the value changes over time very easily because the total height of the bar is very easy to read. But look at the top blue bar. So this is the largest area, largest county, I guess, in Bavaria. And look at the total numbers are going to tell you the variation, but try and figure out if the value there increases or decreases. And it's pretty much impossible because you're looking at this series of bars that aren't on the same baseline. And that makes it really difficult to read them. So a stacked bar is actually worse in many respects than most pie charts. And it's certainly much worse than your standard bar chart. Another thing that's interesting about bars is that they're not immune to the data being difficult. So here's an image from a study run by Sachs and Tversky and others in the late 90s, where they looked at several variations of bars. So they looked at a standard bar chart, and they asked, well, how many more times is the value that's indicated by a dot than the smaller bar there. And then they tried a 3D bar chart. So this is a bit hard to see here because the figure is really bad, but this is like a very simple 3D bar chart. And they found that people had more trouble with the 3D bar chart, which is not surprising, of course, because it's a bit unclear where the top is, and you have this additional dimension here. But they also found that when you added noise to the bar, so this is from a different paper, but it's the same idea. When you look at the bottom, you can see that the left chart here has the dots next to each other, in the bars next to each other, so you can compare them very directly. Whereas the one at the bottom right has the bars separated, and there are other bars in between. And that's a very common thing to have, of course, in a bar chart in practice. And it turns out that when you have not just separation between the bars, but also noise, meaning data, but noisy data that doesn't smoothly change, but that changes erratically, it's actually as hard to compare those bars as it is when you're looking at 3D bars. So 3D is something that people will tell you is a bad thing, and in general, it's not a good thing. It doesn't help you read things. But there are other things that aren't as obvious, like the patterns in the data, that actually make it harder for us to read, or as hard for us to read things as 3D does. So this is just an example here, or a few examples, using the most basic chart type, I suppose, which is the bar chart. There are other examples. I don't want to go into much detail, but there has been some work on what's called staggered animation. When you look at animation, there are certain techniques for how you group things and how you move them and how they help you follow what's going on. And that has been largely debunked. It's not actually true. It doesn't actually work. There is a paper on what's called banking to 45 degrees. The idea there being that you have a line chart and your average slope in the chart should be about 45 degrees. That is still a good idea, but the science it's based on has been shown to be wrong. So that was a mistake, essentially. I don't want to go into the detail here, but there have been some limitations in that study that led to that. And the correct value is much, much lower, but it's not really practical for most cases. You've probably heard about lying with statistics and lying with visualization. You can do that by cutting off the axis on a bar chart and doing things like sizing bubbles in a bubble chart by radius rather than area and so on. But the problem was, for a long time, those were just mostly assumptions. And recently, about a year and a half, maybe 2 years ago, somebody actually did the studies, and they showed that many of these things are true. They really are deceptive. And so I'm not saying that all the things we think are bad actually aren't, or the things that are good aren't, but we need to have science behind it. We need to actually know where that is true. And I've got two more quick examples here that are very, very broad. We've done some work, and by we, I mean myself and students, and others have worked on how the visual representation of the data changes the way you look at it and how you perceive it. And it's staggering how much an effect it has. Would be an entire talk just on that, easily, several talks probably. And then another one that is just endless, and I have no idea where to even start, is color. So color is very difficult. It's a hugely complex topic. There's been a little bit of work in visualization, but it's still very early, and we have a very, very superficial understanding of. So what I'm trying to do here is just to say, well, there's all this stuff out there, some of which we've studied, some of which we've only started to study, and it might all seem fairly simple, but there's a lot of subtlety and there are lots of things that we need to understand better than we do right now. And oh, and I wanted to mention a paper real quick here. I have a paper coming up at a conference that is called Believe at the IEEE Viz conference, which is the big visualization conference that talks about this. So that's why I have an opinion on this, and I thought some of you might get a chuckle out of the title here, An Empire Built on Sand, because I'm trying to kind of say, well, we need to do better with building the foundations for this. But let me now move on to the other part of this, which is about pie charts. And the thing about pie charts is that a lot of people in visualization don't like them. And I gave a talk recently that kind of reflected that. I called that Pie Charts Unloved, Unstudied, and Misunderstood. And I think this is, I still like the title because it's so true. People don't like the academic researchers don't like these charts, and so they just don't, they kind of avert their eyes when they see them and don't even study them. And so we did some work on that and tried to figure out, well, how do they work? And can we learn something new about them? And so by we, I mean my student, Drew Skow. This is Drew with his then girlfriend and now wife, Sasha. He's about to graduate, but he's done some good work on how do different kinds of chart types work and how well can we actually read them. And for a talk recently, he prepared this little image here, Earth versus the pie charts, and it's kind of a fun way of thinking about how we kind of don't really think we I don't know, maybe a lot of people are just scared of them or unsure what they are. And it's easy to make fun of pie charts. So this is a favorite example of mine. This is from Wikipedia again, but this time a bad example. Somebody put all the states in the US, the populations of all the states in the US, on a pie chart. And it's an amazing chart because it's just so useless. Like when you look at Oregon, which is somewhere in the, I don't know, 11 o'clock position there, there's no way you can compare anything there. The slices get too small. There's too much stuff on here. The colors, maybe they don't actually repeat, I'm not sure, but they're so close that you can't tell 50 colors apart. There's just no way. And the fun thing about this too, other than it just being too much stuff and just not very suitable for this kind of thing, is that whoever made this chart realized that there just wasn't enough space up there for all those labels, so they combined the labels into other 16 million people, just other, but they didn't combine the slices. And so it's really interesting how people just don't seem to get that you can't just throw data into a pie chart and it's just and expect it to work. So this was actually on a fairly prominent page for a while. It's now been taken off, but it's still there. You can still find this chart on Wikipedia somewhere. There's also, since another election is coming up, this one is from the previous big one that had this famous pie chart that some Fox News affiliate showed, where the slices add up to 133% or so, 163% even. So it's just more than that. I can't even do math right now. So it's just not a representation that makes any sense. However, even charts that might look like they're kind of the wrong thing at first, they can actually work really well. Here's a donut chart, a combined, like a group's donut chart perhaps even, that shows election results in Alberta. And it works well. It shows you the distribution of the seats in that parliament. And because the values are different, and because, well, and also because they're numbers, but you can easily tell which group or which party has a majority here and how much of a majority they have, and whether they're able to pass laws that way. So this is a useful representation. So the problem is that we have this knee-jerk reaction now against pie charts, but it's not that simple. There's a lot more to them than we tend to think. Now, one of the big misunderstandings, perhaps the central misunderstanding in my humble opinion, about pie charts is how we read them. So there are three different ways of how we might read a pie chart. One is the angle in the center. This is what most people would tell you how you read a pie chart is. You look at the angle in the center, and that's how you read the value. But there's also the arc length, which is the length on the outside of the chart of the pie, of the circle. And then there is the area, which is the area of, in this case, the blue slice there that represents the value as well. And this is also a fraction of the total. So each of those could be the way we read this, or some combination. And so why do we think it's angle? Who decided that? And how well, and again, how do we know that? Why do we think that? Well, let me introduce you to Mr. Walter Crosby Eales. He wrote a paper in 1926 that's called The Relative Merits of Circles and Bars Representing Component Parts. And this was published in the Journal of the American Statistical Association, again in June 1926, so this is now more than 90 years ago. And what he found in this study that was really very limited and very simple, but it was also very early, is that the majority, I think half of his participants, when they were asked, how did you read these charts, they said, I looked at the central angle. And I think of the other half, about half of those roughly said arc length, and the other half said area. The problem with this is that, well, and this was a study that actually had a huge impact back then. There were lots of responses to it, but not to this question of how do we read them, but how well do they work? Because Eales found them to work pretty well for a number of his tasks. So he had a small number of different things he tested, and they worked pretty well. But because even at that time, people were already against pie charts, there was a lot of backlash against it. But nobody picked up on this question of how. So my student Drew and I, we did a number of studies, and we had two papers at the Euroviz conference. I'm showing you the papers here. That was this conference took place in June, I believe. And this is the second largest visualization conference. There's the IEEE Viz conference, and then there's Euroviz. Those are the two main conferences in the field. And what we showed there was a study where we took apart a pie chart and asked people to read values off the chart using just these elements. So the problem with what I just talked about is that you can't separate angle and area and arc length usually. So what we did was we tried to do it anyway, and we started by having a regular old pie chart here. We just used a single slice well, two slices, but one we asked about, and because we needed to keep this simple. And then we also had a donut chart as a comparison. And then we created separate charts that we basically said are only a single visual cue. So the bottom left here is only arc length. So you can see that there's just that ring there, and the only thing you can see there, you can't really see the angle because we've taken out all the angle cues, and you can't see area either because of course there's some area here, but it's not really a way of reading area. And the bottom right one is just area, and this one is interesting because what we did here is we took the circle, we filled it up like you would like a fishbowl with water with this color to represent that fraction as the area. And then I should also say that all of these were rotated randomly. You would only see this particular shape maybe once in the entire study, and then it would be rotated all kinds of ways. And I expected that to be really bad, but it turns out that it actually did much better than expected. And then our last two types are what we call angle only. So the bottom one here is like a pie chart where we took out the pie essentially and only showed the edge between the two slices. And if you see the little gray thingies there, they might be hard to see on your screen, but those point towards the slice we were asking about, because otherwise it's not clear whether we're asking about the larger or the smaller one. And then the top right version here is basically the variation of the donut chart, where we took out everything out of a donut chart that's not the edge. and then did the same thing. Now, to show you the results, I'm going to use a similar chart to what I showed you before earlier when I talked about the Cleveland and McGill paper. This is going to show you error, which is now a signed error. That means it's a bias. And but actually, so this is basically about bias here. And what this means again is that this is the mean or the average here. This little dot. And then the extent is this confidence interval, which basically means this is where most of the data is. And we're very sure that most people would stay within that range when they answer. This is just to constrain the statistics a little bit here. And what we find is that when we look at the deviation, and this is now going both directions, up and down, so we're not just summing them up in the same direction, is that they don't differ much at all. So this is practically no difference here between the pie chart and the donut chart, which is interesting. We also find that this arc-only condition here works very much the same. So as long as these intervals overlap, we consider them to be the same. The area only chart does surprisingly well, and it looks very similar to the others. And what does much worse, because you can see that their error interval is much larger, are the two last ones. These are the two angle-only conditions, the two angle-only charts. And so, so I've added in this ribbon here so that you can see the comparison. So this means that the blue ribbon here is the comparison with the pie chart, and as long as all of these other intervals overlap that ribbon, it means that they're not actually significantly different or statistically significantly different from that from the base pie chart. Now, when we look at this in a different way, here we're looking at what's called the absolute error, and the absolute error is now like that earlier paper I showed you that summed up all the error in the same direction. So whether you were above or below the correct value, we would always sum it up into the same direction. And when we look at the pie chart here again, we can see that there's a certain value. This is percent different. I mean, percentage points different. So that means that people on average were about 4% off. And that's reasonable. That makes sense for a pie chart. That's not surprising. What's interesting though is that the donut chart isn't much different at all. So this is a slightly bit higher, but it's overlapping for the most part. I think 2/3 is overlapping. So you can see that this is not a significant difference. The same is true for the angle. I keep saying this wrong. The arc length only chart that looked extremely similar to the pie chart, and our friend the area only chart, which is surprising again because I would have expected that to be much harder to read, but people did a surprisingly good job of that. At this point, maybe I should also say that maybe I'll explain later how this actually is run. And then I'm going to step back here a moment. So the way we ran these studies is we had them posted on a thing that's called Amazon Mechanical Turk, which is an online platform where you can give people small tasks and you can pay them small amounts of money for it. And this is useful because it lets you run a study like this fairly quickly. You can just throw this out, have 100 people do it. They take 15 or 20 minutes answering all these questions, and then you get the data back within perhaps a day or so, which if you did a lab study, it would be impossible. And so when I keep talking about people doing things, that's what I mean. So there are people who were mostly in the U.S., but they were scattered all over the place, and they would do these tasks and then give us these numbers, and we then take those and do some statistics on them. This is the thing that we're looking at here. So we're looking in general at people who aren't precision experts at all. They're just random people, and they were able to read these charts surprisingly well. So, but to get to my point here, so the first 4 of these deconstructed pie charts here were all basically the same. There's really no difference here. And then what's very different here is the angle-only conditions. So when we're looking at the angle-only pie chart and the angle-only donut chart, those were much, much worse than the others. And now you could argue that the angle-only chart is very unusual, and that is true, but it's also the area-only one is also very unusual, and even the arc length-only one. And people just did so much worse here, and this is a huge difference when you compare this to the baseline. This is a variation of like several times the mean value. I think it's like more than 3 times the mean, and easily like I don't know how many standard deviations this is. I should probably do the math on that. But this is a very clearly significant difference. I shouldn't say very significant because that's not an actual thing, but it's a very clearly significant difference. So that tells us that this idea that angle is the only thing, the only way we read these charts is clearly not the case. This is not true. This is kind of the smoking gun here. Actually, I have another one that's a bit more of a smoking gun because it's a bit more obvious. But I think this is a very interesting chart. And again, it took 90 years for somebody to ask this question again and actually look into this and do some science on it. I've also here, this is a minor variation of what you just saw. I compressed the pie chart into a single dot, and that gives me slightly narrower intervals, but that's just a statistical technicality here for people who are familiar with confidence intervals so that we can do a proper comparison here. So what did we find? I'm going to show you this in a slightly different format here by showing you the images again. And this is a simplification, but I think it's useful to show this. So we found that the pie chart and the donut chart are pretty much the same. I mean, they're not exactly the same, of course, because we're doing this across many different people and so on, but they're very similar. We also find that the arc length only and the area only charts are very similar. And each of those are similar to the full pie and the full donut chart. And this is interesting because it's not just a matter of what are the individual cues, but do we use one of them or several? And that's still a bit unclear. But what we can see with a lot of confidence here is that each of those is much better than only the angle. And so that, again, is a very clear indication that we should be looking at this as being just debunked. We know that we're not using angle alone to read these charts. Now here's a slight variation of this. Here we're looking at the bias, the error, that signed error in each of those types. And this is not very interesting at this point. So there's a bias, meaning that is there a consistent over or underestimation using each of those types? And I'm only showing this here to kind of introduce the idea because you will see in a moment where this is useful when we're looking at a bit of a more applied version of this. But what's interesting is that none of these had a very significant bias. The area-only one looks like it does, but it turns out that it's not actually true when you do this little thing here where we compress the pie chart, which is our reference here. What we did do, though, is we looked at the same thing with donut charts. And I'm not going to show you the detailed data here. I'm just going to show you what we compared. So we had these donut charts. We started with a pie chart, and then we basically drilled a hole into it and made that hole bigger and bigger until we ended up essentially with the arc length only one. And what we found there is that they're all pretty much the same. There are some minor variations, and the last one here actually did a bit worse than the rest, but they're very, very similar. So this idea, again, of the central angle being the way we read these charts is clearly not true, because otherwise the donut chart would be doing worse than the pie chart, because we're taking out that center part that would be important for reading a donut chart. Now, having done all that, we can do something that we don't really do a whole lot of in visualization, which is to do some actual science. And we can make predictions. We can now say, well, we think that it's not angle. What does that mean? What do we expect for certain kinds of things that people do when they do information graphics, especially? So here's a small collection of things people do. One is they use pie charts with one slice being larger than the rest. So we created a version of that. We had a colleague of mine calls this the pie chart was a hat, but the idea is that it has a larger, the blue slice is larger than the actual base pie. And we expect that to be an overestimate. And then people also explode these charts. So these exploded pie charts mean that we move pieces apart, and we did a version of that. And here we didn't really we didn't think that there would be a difference, at least not a bias, but we figured that there might be a difference in precision. And then I think people do a lot in information graphics is they make pie charts out of things. It's like this brain shape here. This is a pie chart. The weird thing here is also that they use the white part as the 80%, and the blue for some reason is kind of the rest. But anyway, so we created these two charts that were irregular charts. So this is not a 3D pie chart in the bottom left there, but it's a elliptical chart, and the other one elliptical pie chart, and the other one is a square. But both these were drawn as if they were pie charts, so we're not changing the area or anything. And I mean, according to the shape, we're just using the angle. And here we would expect more error if what we saw, if what we found was true. And then finally, we had a baseline pie chart to compare everything to. So what did we find? Well, we found that this is now looking at the bias relative to the pie chart. So I've skipped a few steps here, but the main thing is to compare the systematic deviations of what's called the bias, basically. So whether you overestimate or underestimate systematically to the pie chart. And what's interesting is that this guy here, and this is now my smoking gun, is that the larger slice leads to a very significant overestimation. And that is interesting because if it were only about the angle in the center, that would not make sense. Why would that be the case? But because it's either area or the arc length, and both increase with the radius, there clearly is an effect here, and we see that in the overestimate. We can also look at error a bit, and we see that. Actually, I think I have the error here. So this is now the absolute error, so we can see the deviation. And interestingly, well, I guess it's not that surprising that the exploded pie chart has a high error, though it's a bit more than what we expected it to be. And then the last two here, the square and the ellipse, both have very much, very clearly higher absolute error, which again tells us that there is a weird correlation or a weird interaction here between the arc length, the area, and the angle. Because again, if it were only the angle, we should be able to read this without having high error. So all of this very clearly points to the angle not being the main criterion we use to read this. There's one more little piece of personal history here, perhaps. We did a student of mine and former student of mine and I did a study back in 2010 where we looked at a number of different different charts. And in particular, we looked at these, what I call a square pie chart on the left there, what's essentially a stacked bar chart, and then a pie and a donut chart. And we found the same effects, but back then we didn't really know what to make of that, so we kind of ignored those results. But they perfectly match what we just found, what we found last year, I guess, in these pie chart studies, in that there's no difference between the pie and the donut chart. And interestingly enough, the left one there, which is the waffle chart or the square pie chart, does much better than any of these. And the bar chart, or kind of the stacked bar in a way, because this comparison here is along the line, is much worse than any of those. It's the worst of the charts, actually, is the bar. So to summarize this a little bit, we can say, after having done all this, and having done some actual science here, so this is actually running studies and trying things out and teasing things apart, we can say a few things about pie charts and how they can be used in practice. First of all, we can tell that it's a bad idea to change the size of the slice that you want to emphasize, unless, of course, you want to have people to overestimate it. But that's what it does. It leads to overestimation, and it's a very systematic, very strong effect. people will overestimate the value, and even if it's just a small difference, like you can see here. What's also bad is exploded pie charts. I don't think that was known at all before. And of course, what was suspected, but I don't think was known, was irregularly shaped pie charts are bad. So those leads to much larger error than any other kind of pie chart. And lastly, the fun part here, for me anyway, is that donuts are fine. They're no different than pie charts. So if you're going to use a pie chart, you might as well use a donut chart. There is no difference between them that we have been able to find. And you can just use them with abandon. They're fine. Don't listen to people who tell you otherwise. But the main thing, and this is really where it's kind of basic science, is we can say it's not angle. We know that now. It's very clearly not angle. We have not shown entirely if it's arc length or area. I'm still working on that. And my personal opinion, that isn't based on any science at this point, is that it's actually more likely to be area than arc length. But we've also seen some patterns that point to arc length. But I would be surprised if the arc length was actually the thing that we use for that. Area seems just much more robust and much more likely to me. But we don't know. So we know one thing now. We can rule out one, which is the angle. And now we need to figure out what's happening to the rest. Now, I have a bit of a history here with these kinds of things. So pie charts are kind of the outcast of visualization, and the pariahs, the untouchables, perhaps is a better term. I've also done work with Drew Scow on embellished bar charts and how those work or don't work, and whether they're good or bad. And I did some work with Steve Rose and Steve Canary on what's called isotype, which introduces a lot of what you might call chart chunk into a chart and adds a lot of things to it that you wouldn't see in an officially considered good chart. So I like to think, I don't want to compare myself to Mother Teresa here, but it's not that far off, perhaps. Now, the main thing, though, other than being a jerk here about comparing myself to saints, is that I think what's important is we need to understand, and we need to ask more questions about visualization. So when you read a book, or when somebody tells you something, and especially when they're very convinced about it, ask them, well, how do you know that? Why do you think this is the case? Can you point me to some actual research? And a lot of this, and I didn't actually touch on this in this particular presentation, but there's a lot of aesthetic judgment, and many of the things we think we know very nicely mesh with those things that we believe, but they're not, and that we think we like in terms of aesthetics, but they're not necessarily true just because of that. And with that, I'm going to hand things back to Bill, and I'm happy to take any questions you might have.
Well, Robert, thanks so much for that excellent presentation. We'll get started with today's Q&A session, and I want to thank the audience for their participation. We've had a great many questions that have come in during the presentation, so we'll do our best to get through all of them in the time remaining. And during this Q&A session, we'll leave this screen up with contact information for Robert if you'd like to contact him following today's webinar. So let's get started. Robert, this was all about pie charts. At the end of the day, are pie charts still okay to use so long as we don't use, for example, just the angle-only version?
Right, yeah. So the thing that I sometimes get people confused about is that I'm talking about comparing different parts of a pie chart to, and also doing a bit of comparison between pies and donuts. But when you look, there is some literature, and that's fairly well established, that when you compare bar charts and pie charts, the bar in almost all cases does better. So if you're after precision, the bar is the better choice. But in many cases where it's not that important that you have ultimate precision and that people can read like values off of the chart, the pie chart is just fine. I think of course there are a few limitations. Like don't use too many slices. If you have a small number, like maybe up to 7, 8, something like that, it's still okay. But if you go beyond that, it very quickly gets problematic. Also, if you're if your values are very similar, the pie chart is really useless because they all look the same. But if you have a nice distribution, like in the chart I showed at the beginning with the different parties and their seats, then you can tell the values apart very easily by that. Then they're also fine. So in many cases, I think they're very useful, but that's not necessarily my message here.
Okay, but let me clarify something that I think I heard you just say, and it was also a question from the audience. And that is, since when we use pie charts, we're generally trying to point at one or two or just a few of the segments to draw the viewer's attention. Does the perceived error increase with the number of slices? Should we intentionally try and reduce the number of slices to decrease perceived error?
That's a good question. I don't know. I don't know if there is literature on that or research on that. I would expect, certainly if you go beyond, say, a dozen slices, you're in kind of hopeless territory because your slices get so small that it's impossible to tell them apart. So there certainly is an effect when you go to a large number. If you're talking about a small number, then it's harder to tell. So I'm not entirely sure. But to be on the safe side, I would say yes. You certainly want to keep the number as small as possible. Like, what do you actually need to show? And when you have too many things in there that you don't even need because you don't care about them, then just group them together and make them an other category, and then just show that as a larger slice.
Okay. Now toward the end of your presentation, you talked about some of the other unusual ways to present bar charts with stacked dogs and fish and that sort of thing. And there is a question from the audience that, well, what do you know about the efficiency or of other types of complex visualizations like heat maps or chord graphs?
So what we studied in particular is this thing called isotype, which is the stacked fish, and we compared that to different kinds of things, and we found that for the most part they're just as good in terms of precision as the bar charts, but that's also somewhat limited to our data, and they work better for memorability. So people remember them better than a bar chart because we give them something to remember. There are other kinds of charts that are, in terms of readability, the chord diagram in particular can be very difficult when it's too much, when there are too many crossings and too many categories, but it can be very effective when it works. So there is a class of, I have a whole talk on that, there is a certain class of visualization techniques that works really well in very few cases, but does not work at all in most of the cases. There's a technique called connected scatter plots that works like that. I think, and most people disagree with me here, but I think that the chord diagram would probably go into the same basket. There's also the heat map. I don't know the research on the heat map. I haven't seen anything because it uses color so much. Well, I do see a lot of really poor uses of color in heat maps. Especially when you look at red-green contrast. It's not just that colorblind people can't see that because the most common color deficiency is red-green, but also because the differences are really hard to spot. So there's a lot of things that can be improved about heat maps from what most people usually do. And then the question is, what are you trying to get out? If you're looking to get out of the chart, if you're looking for patterns, a heat map can be very effective. If you're looking at small differences or judging differences, I think it's very difficult because you're looking at color as a representation of value, which we know is very imprecise and just kind of gives you a rough idea but does not give you much detail.
Well, thanks for that answer.
But that's a good question because there's a lot of gaps here that we need to fill in.
Okay, and I believe in your answer you actually said that there are some circumstances where particular types of visualizations are better understood than others. So are there cases where pie charts are specifically should be used, and how does this simply play into the issue of the aesthetic sense of the person preparing the visualization? Isn't this really a judgment call, or are there specific cases where we should be picking pie charts?
Yeah, so there are specific there has been a little bit of work that looked at how you compare. First of all, the main thing you should be doing in a pie chart is compare the parts to the whole chart, not the parts to each other. That's a fairly well-established kind of rule. I'm not sure if it's really 100% backed up by research, but it's something that people tend to do. And then the one thing that people have shown in a paper, and I forget the name of the paper or the authors right now, but there's a fairly famous paper that looked at people combining slices. So if your task, what you're looking for is not just a single slice and compare it to the entire thing and say this many percent did this, but if you're likely to combine several of them that are attached to each other or next to each other, then the pie chart works really well for that. What also works well is to understand that part-whole relationship. So when you're looking at what fraction of the total is this particular category, then that's actually easier to tell than with a bar chart. Sometimes people just redraw a pie chart as a bar chart, which gives you more precise comparison between the categories. But when you're comparing the category to the whole, it's actually much harder because you can't actually tell how much the total is. And then I forget the second part of your question about, you asked about specific tasks, and then...
Well, to what extent is it just really up to the aesthetic sense of the person preparing the visualization versus some scientific guidance that says use pie charts here?
Right. So I think that's an important part of it, but it needs to be informed. So if you know that you're doing something that the research tells you shouldn't be doing, but you think it's a good idea because you're after a particular thing, and especially you're after particular aesthetics, then do it. That's my opinion. But you should know why you do it, and not just say, oh, I'm going to use a donut chart without knowing anything about it, just because it looks cool. So you should be informed about the things you use, but you shouldn't let that keep you from using them. Okay,
good response. Now, you may have touched on this, and I hope I didn't miss this, but did your research also touch on the maximum number of values that should be included in a pie chart? Is there a maximum number, or aside from that, that eye chart that you showed about states, is it pretty much up to the designer?
Right, so 50 is certainly too many. I don't think there is a well-established number. The usual number you hear is somewhere in the 5 to 7 range. That has to do with this idea of our short-term memory and how many categories we can remember. But I would say, depending on, it's probably in that range. So maybe up to 10 is probably the upper end. That's useful if you're, let me qualify this a little bit. So if it's a static pie chart, then there's a very strong limit, and that's probably even less than 10 slices. But when you have interaction, when you can mouse over your chart and it tells you what the value is, then you could probably go a little bit higher. You still shouldn't do 50, but you can do a lot more, or you can do a few more, not a lot more. But I'm not aware of research in that direction. It would be very useful to do that for sure.
Okay, well, thank you. Now, you definitely showed us that using just the angle or focusing on the angle was not the way that people actually best perceive this information. What about percentages as opposed to angles? Is it easier to represent these as percentages as opposed to giving actual values around the outside of a chart?
Oh, so you mean the numbers that are represented, that are shown as numbers?
Yes. Instead of showing actual values, always default to percentages, for example. Right.
So that's an interesting, I mean, of course you want to show, so yeah, in general, I would say that that's certainly what you should be doing, because you're looking at fractions. So you're always looking at a part of something, like you're saying this many % of people did this or that, or this many of our website visitors clicked on this button with that button. And so you're looking at a part of some collection. And so you're going to always have a percentage that you should be able to show. But you can also, of course, show the total numbers, especially if that's dollars or if it's some other value that's meaningful as a total number. But the chart itself, like both the angle and the area and the arc length, all represent that percentage of the total circle.
Right. Right. Either way, it's going to look the same. The question is,
right.
Would one be more clear than the other? But I understand. Thank you for that response. Now, you talked about the method that you used for conducting this study. Can you tell us a little bit more about that? Can anybody take part in them? And the other part of that, I think, is the audience would like to know where can they go to see these papers that you've talked about, or simply to find more scientific research on visualization in general.
So the last part of this, where to find more research, this is a little bit difficult because much of this is published in journals and at conferences that also tend to now publish their proceedings in journals that you have to have access to. So if you're at a university, you almost certainly do, but otherwise it's a good idea to just look at some of the websites where people write about this. So there's, of course, my website. It's called eagereyes.org. There's places like flowingdata.com, Nathan Yau's website. He sometimes points to research. You can follow people on Twitter that do research, people like Tamara Munzner and Jeffrey Hare and others that also talk about their research. I'm blanking on somebody's name right now who would be an interesting person to follow as well. And so there's a number of websites and blogs where you can find that. And they tend to point to the places where you can read those things without going through some paywall of some journal. And then in terms of the studies, so there's the Mechanical Turk platform is an Amazon thing. You can go to mturk.com, mturk.com, and you can log in with your Amazon credentials, and then you can just look around at all these different kinds of things that people want you to do. And many of those are, well, there's just an enormous amount of different kinds of things. And for the most part, like almost all of them are not studies, but they're like little tasks. Look at this picture and tell me if this is actually the same thing as the description says, and so on. So this is meant for tasks that a machine can't do, but that people can do very easily. So you would have to basically watch that to find the studies. What I tend to do is I don't tell people that I have these studies running on Mechanical Turk, because I'm trying to not taint my results with visualization people trying to take part in those studies. So it's easier to kind of keep that separate. But there are a few places where you can find those. There's something called like the Worldwide Laboratory or something like that. I keep forgetting the exact name. But what they do is they publish studies there, and you can just take part. Oh, and there's a Reddit, a subreddit that's called Sample Size. When you go to that, people publish links to studies there, and you can just go through those and either answer surveys or do little tasks, and then the data that's collected from you as part of this goes back into somebody's research. So there are a few places like that, not necessarily for my particular studies, but if you're kind of interested in just seeing what those things look like, there are a few places like that.
Okay, well, Robert, thank you, and I'm going to put this back up because would you just tell us, please, about these links? I think people are going to want to be interested in following these links.
Oh, sure. Yes. So the first one here is on my website. It's called eagereyes.org. It's kind of a short link that goes to the pie charts page there, so you can take a look at that. It's a bit. This is actually pointing now to the most recent papers, and then there's my Twitter handle. And again, my website. There's also my email address. So if you have any questions, feel free to email me. I can be slow sometimes to respond, but I'm happy to answer questions via email. And I should also mention again, there are a number of other places on the web, like Flowing Data. There's Visualizing Data, which is spelled with an S, because it's Andy Kirk in Great Britain. And those are good places. Carlos Scheidegger, if you Google his name, he has a blog where he sometimes talks about research. He doesn't blog very much. There isn't a lot of science blogging, unfortunately, in visualization, but there are a handful of people. Alberto Cairo, maybe I should mention him too as well. So Alberto has this website called The Functional Art, And so that's a good one to go to as well. He talks a lot about data journalism, but he also points to research at times.
Well, Robert, thank you so much for some great answers to some very good questions. And for those of you who asked questions today that weren't answered, we'll be sending those to Robert and the Tableau team so they can follow up with you after today's webinar. You know, I have just a few quick announcements. If you'd please mark your calendar for September 27th, that's our next DSC webinar. What does IoT Edge Analytics look like by Dell Statistica? Also remember that today's taping will be available for on-demand viewing later today and can be found on the home page of Data Science Central in the Webinar tab located at the top of the page. Well, this brings today's webinar to a close, and I'd like to thank our audience for their attendance and thoughtful questions. A special thanks again to Tableau for their sponsorship and our speaker today, Robert Kisara, for his insight into today's topic. Now, my name is Bill Voorhees, and I'm very pleased to have been your host for today's event, and I look forward to seeing you all again on September 27th. Have a great day.